Hello, Chile. The paper is performance comparison of linear and nonlinear recording for massive meaning. Please. According to us. You have 12 minutes, and 3 minutes are for discussion. Already started. 5 minutes. I have to make the focus. With all the presentations. Remain here.
With Malaya Chile, supervisor, Dr. Mukuba and Dr. Pile, and today I'm presenting performance comparison of linear and non-linear sequence massive memory. This is the outline of
F5 to have a screen.
You can click on the symbol down there on the right hand, down the last symbol, and then you are projecting the whole screen. Yes.
for that. And as I said, this is not Malaya TV, and the topic of my paper is performance comparison for linear and non-linear performance for massive memory. And then this is the outline of what I'm going to talk about. Telecommunication industry has a growing demand for comprehensive fixed broadband and broadcast wireless network, wireless communication services. As you can see, the first picture on the slide depicts the common wireless communication equipment that includes most, I think all of us here do have a cell phone, you do have wireless mouses and remote controls, so it shows the build out of the data. And far left is the communication technologies that we use daily. And users of wireless communication have increased exponentially in a few years, and these users generate trillions of data that need to be taken care effectively and more reliably. And this resulted in the evolution of wireless communication, which dated back from 1980, where we first learned about the first generation. And in the first generation, that is when the cell phones could only make a call. The second generation is where they introduced SMS on top of making a call. The third generation is where internet was introduced into the cell phone. Fourth generations, the videos were also introduced. And then in the fifth generation, now we're making calls, we're using SMSs, videos, and now in the fifth generation, we are more concentrated on the speed and the reliability of handling the data that is being generating by the users. So as I said, in the fifth generation is the current. The fifth generation promises us the increased data rate, it reduces latency, it enhances energy savings, it also reduces cost. Okay, and these are the technologies that are making up fifth generation. It's not only this one, there are more than this, they couldn't fit. So only listed few like the Internet of Things, the Cloud RAN, millimeter waves, also including the massive MIMO, and my study is more on massive MIMO. So massive MIMO has gained a lot of so massive MIMO has played an integral role in transforming the terrestrial wireless communication, but it also has its own technical or complexities. Those complexities are listed that side, but then the one that I'm concentrating on is the pilot contamination, but I'm using pre-codings to solve the pilot contamination. So the aim of my study was to compare and perform linear precoding algorithm with non-linear precodings in the context of massive MIMO. And my objectives were to compare linear and non-linear precoding algorithms that include in the list of the linear precodings. I chose minimum mean square error, and I also chose a Newman series approximation. And under nonlinear, I chose lattice reduction under the lateral lobes, and then I also chose Tomlinson-Harashima precoding. My other objective was to involve the effectiveness, also to evaluate the effectiveness of different precoding techniques in terms of bit error rates and signal to noise ratio performance measures. As I said, I'm concentrating on precoding. So precoding is the process of applying the linear and non-linear transformation to data signal before transmitting. It also aims to maximize the signal to noise ratio and minimize the interference and distortion. These are this is the matrix to calculate the minimum mean square error, and then there are a lot of calculations that were used to evaluate the MMSE precoding. I also use Newman series approximation. Minimum mean square error suffers, it works well, but it is complex. So Newman series, it's introduced it to minimize the complexity that comes with the minimum mean square error. And there are a lot of equations that we use, but I only chose this one for demonstration purposes. The non-linear precodings, I've chose the Tomlinson-Harashima precoding. It's a technique that was first designed for channels that are having inter-system interference. And it's divided into two. There is the centralized CHP and a decentralized CHP. And these are the formulas that we use to calculate centralized, decentralized CHP, and this is the one that we use to do our calculations for centralized CHP. And the difference between centralized and decentralized CHP is that centralized uses the scaling matrix at the transmitter, while decentralized uses the scaling matrix at the receiver. This is the method that I followed when I was conducting my study. I first studied the linear and linear precodings, like the one that I listed there, and I used MATLAB to simulate the signal to noise ratio. And then I used those results to do the comparison between the linear precodings and non-linear precodings. This is the system model that I used. It's the relationship between the transmitted information there as X, and then the received information there as Y. And then that's the noise, and then H represents the channel, the communication channel. And these are the results. So I use those mathematical calculations to plot this distribution. I change those mathematical into MATLAB so that I can be able to get these results. So figure 4 and figure 5 we simulated using 16 transmitter antennas and then at different modulation scheme. Figure 4 was when I was using 16 gram, and then figure 5 when I reported using 64 gram. So when I compare the performance, you can see that the last reverse it's much better compared to minimum mean square error and the Newman series application. And if you can see even there, it's much better, but there's also an improvement of about 8% between the 16 antennas used and between the 16 gram and 64 gram. And I also did my comparison using I increased the number of I also increased the number of transmitting antennas to 32. I had 32 antennas at 16 qm and then 32 antennas at 64 qm. And then with what I found, or with my results, it shows that the lateral lobes still performs better compared to other precodings, mostly with the linear precodings, but it comes with a lot of calculations and it's very complex to work with it. This is my other result, whereby I compare two linear precodings, which is the MMSE and the NSA, compared with the Lancer reverse and the THP. As you can see, that THP also works better than the lattice reduction, which is LLL. So the conclusion, this paper compared a basic linear precoding, which is the basic linear precoding MMSE, the matrix inversion approximation, which is NSA, with the non-linear precoding, which is lattice reduction at 0 function, and then the Tomlinson harassment precoding for massive system. Simulation demonstrates that non-linear LLL and THP method proves performance when improves performance when the ratio of base station antennas to users is modest yet computationally intensive. Meanwhile, linear precoders like MMSE proves to be less complex with performance degradation under specific scenarios. Furthermore, further exploration is required in the examination of the THP method. Thank you.
Questions?
Thank you for your presentation. I see the system model that you presented to us, but I don't missed it. What channel model did you actually use to which propagation effects are the signal subject in your system model for the different signal paths? Is it Gaussian or Rayleigh or Gaussian or?
We're using Rayleigh here, the range, but not in.
Thank you. Questions? No, thank you very much for the presentation. It's yours. Okay. The second presentation is done by Dr. Yashil Morar, a study of large intelligence applications in fading channels.
Good morning, everyone. My name is Yashil Moral. I'm a master's student in electronic engineering at the University of KwaZulu-Natal. And today I will be presenting our paper titled A Study of Large Intelligence Surfaces in Icecet Fading Channels. So just as a brief outline, we'll first introduce some background concepts. We'll then state our contributions to the research. We'll then look at the work that we've done. We also provide some simulation results. We make some observations and discussions based on them before concluding the presentation. The advancements made in next generation wireless networks have been substantial thus far, with many 5G networks having already been launched in many countries around the world. Despite this, much work has been devoted to beyond 5G or 6G networks, as the current and future demands and requirements on modern wireless communication systems continue to increase year after year. It is evident, therefore, that a drastic change is required to meet these demands. Large intelligence surfaces provide a new paradigm shift in this respect. An LIS is a large contiguous surface comprised of low-cost passive reflective elements. The LIS reflects the incoming wireless signal by adjusting the phase shifts of each of its reflective elements, enabling a controllable wireless propagation environment to enhance signal strength and quality. Now there's two main configurations of the LIS that have been proposed. The first is the dual hop or non-access point scenario, in which the LIS is placed inside the wireless environment to reflect the transmitter signal. The second one is the access point based LIS, in which the LIS is placed close to the transmitter, such that the LIS virtually acts as the transmitter of the wireless signal. Now there are many motivations for using this. I won't go over all of them, but the main one I want you to see is number 3. It's been shown to produce significantly better error performance gains in comparison to the non-access point configuration. So if you can take a look at the diagram, you can see that the LIS is actually able to provide a very dominant line of sight component, assuming a non-line of sight or weak line of sight environment, which is quite a big advantage of the LIS in that it can provide additional line of sight paths via its reflective elements in environments which are very weak in terms of its line of sight or blocked or non-line of sight. Now, by virtue of having a line of sight component, what this means is that studying these systems in Rayleigh fading has become redundant. And rather, it is more correct to study these systems in fading channels which consider varying degrees of line of sight. Therefore, in this presentation, we investigate the error performance of the two fundamental LIS-aided schemes, the non-AP and AP schemes, in Rayleigh fading channels. We also provide the theoretical analysis of the symbol error probabilities of both schemes under Rayleigh fading. and we provide computer simulated results in the form of symbol error ratio versus signal to noise ratio graphs. Okay, so let's just have a look at the first scheme. In the first scheme, as I mentioned, we placed the wireless in the LIS inside the wireless environment. We transmit a total of log2m bits, which selects a data symbol, either mquam or mpsk. The Ricean fading channel vectors is two of them, given by h and g, and the noise given by n. Okay, you can't see on the bottom, but we phase shift each of the reflective elements to maximize the SNR, and it results in a simplified channel given by A. The receive signal is given by Y for a given SNR denoted by rho, and the maximum likelihood detector is given to estimate the transmitted information. In the AP scheme, as I also mentioned before, we place the LIS close to the transmitter such that it acts as the virtual transmitter of the wireless signal. Here again we transmit log2m bits, but this time it selects a phase value to phase shift all of the reflected elements by a common value. Notably, we consider an unmodulated carrier signal with a single Ricean fading channel denoted by G and the noise denoted by N. And here we phase shift the reflective elements according to the phase value that is chosen. And if you take a look at the receive signal, this actually transposes into the transmission of an MPSK symbol through a channel given by B. And in the ML detector, we only have to detect this virtual MPSK symbol. In the theoretical analysis, we first note that the instantaneous received SNR is given here, and we note that an arbitrary Ricean random variable has the statistics given by its mean, its second moment, and its variance, where K denotes the Ricean K factor, which represents the degree of line of sight, and I0 and I1 represent the zero and first order of the modified Bessel function of the first kind given by this sum, with Z being the arbitrary order. And from here we employ the moment generating function approach along with well-known integrals to evaluate the symbol error probabilities of each scheme. So we'll just take a look at some simulation results that we managed to generate. In figures 1 and 2, we have the SDR versus SNR curves of the LIS AP and non-AP schemes for 64 reflective elements, a modulation order of 4, so 2 bits, and varying K or varying degrees of line of sight. Two things. Firstly, for the non-AP scheme, we only assume MQAM data transmission for the study. And as you can see, we also plot the Rayleigh fading curves just to show that Ricean fading at K equals 0 is an equivalent Rayleigh fading channel. So as you can see, as we increase K on the line of sight, there's obviously an improvement in error performance. However, this improvement in error performance is far more prominent in the non-AP scheme than it is the AP scheme. Now, I mentioned before that the AP scheme has been shown to produce significantly better error performance results. However, given what we see here, it seems that if the degree of line of sight is high enough, the non-AP scheme may produce a better error performance than the AP scheme. Or the non-AP may be able to produce a better error performance than the AP scheme. So I thought that's just a very interesting observation and trend that we've seen in our results. So to conclude, in this presentation we provided an investigation of LIS-aided schemes in Ricean fading channels from an error performance perspective. We also provided the mathematical framework for the theoretical symbol error probabilities of each scheme. We envision and hope that our paper will provide a solid foundation for new LIS-aided schemes to be studied by correctly considering Ricean fading channels, or in general, fading channels which consider varying degrees of line of sight. So some future work includes, but not limited to, the analysis for correlated channels, the transmission assuming discrete phase shifts, closed form Ricean distributions, the analysis for a low number of reflective elements, and finally, transmission assuming partial or absence of channel state information. Thank you.
Thank you very much. Questions, please? Time for the questions. If you have.
Got a quick question.
Yes.
In terms of your simulation results, that's looking very promising. I'm wondering how close is that getting to the ideal case? And what would be your ideal case for the SNR that you're trying to achieve? What would you say is like the main limitation?
So it's not necessarily about achieving a specific SNR. We just wanted to provide a framework to study these systems in Ricean fading channels and sort of just observe a trend for varying K or varying numbers of reflective elements. There's more results in the actual paper, we just chose them.
So one can put in an antenna with a different design and then apply your routines.
Okay, so that's not really my field of study, like antenna design and stuff. This is more like the physical layer concerned with the transmission of bits, data. Yeah.
Thanks.
Yeah, but from a practical perspective, I think that's something to consider is now the actual antenna design of it and things like that.
That's a useful tool that you've got.
Yes, thank you. Like you'll probably be more laid up in the field, so can you maybe just briefly touch on how the LIS surfaces relate to RS surfaces, the reconfigurable surfaces, is the one in subclass of another one, or what's the relationship there?
So the reconfigurable surface is just any surface that is able to reflect the transmitted signal. The LIS is kind of a collection of RISs. So I'll just take you back here. So each individual element may be classified as an RIS. The entire surface which comprises the RIS, as you could say, is a large intelligent surface. Okay, thank you.
Other questions? No, thank you very much. Presentation. Next presentation will be done by Joseph, design and performance analysis of miniaturized circular arc slotted up antenna for ultra wideband applications.
Good morning, everyone. My name is Joseph. I'm presenting on paper, design and performance analysis of miniaturized circular arc slotted patch antenna for ultra-wideband applications. We all know the world is tending to IoT, where everybody wants to connect a device online. Our phones, we want it to be online. We want our cars to communicate with our cars. We want in our homes, we want our homes to be smart home, where we can talk to maybe our toasters, our ovens, whatsoever we have at home. We want them to communicate together. With these challenges of every device wanted to be connected online, we discover that there will be issues of congestions. How do we actually solve this problem? What are the ways to actually solve some of these challenges? I'll be taking us through this outline in this presentation. We'll be going from introduction down to the references. The issue I've actually bring earlier on, we discovered that with congestion on the network, what are the pathways to bring solutions to this? UWB actually refers to communication technology. It utilizes a large portion of the radio spectrum for high-speed data transmission. According to FCC, this range of frequency is from 3.1 gigahertz to 10.6 gigahertz. Patch antennas are actually printed antennas that utilize PCB technology. There are some key advantages. They are low cost, they are lightweight. They can be easily integrated to our printed circuit board because they use the PCB technology. You can customize them to the range of frequency you want them to work in. There are several application areas of these UWB antennas. They're used in wireless communication because of their high speed data rates. They are used in wireless communication. They are used in radar system for ground penetration radar. These antennas can actually penetrate ground surfaces, rocks, so on and so forth. They are also used for true world imaging. It can be used for rescue operations where, because they can penetrate walls, they can be used for rescue operations. They can be used for military applications and so on and so forth. Also for medical imaging, the research it has been used for breast cancer detection, tumor detection, and so on and so forth. But these antennas actually have some key challenges. Some of their challenges is they are narrow band in their design, they have low gain, they have size and space constraint because we want to integrate them into PCB, so they have size and space constraint, and also their range of frequencies is actually related to their size. In literature, there are some key existing solutions to these challenges, to the earlier challenges I've listed here. Some have brought solutions to how to solve the problem of narrowband and so on and so forth. Some authors in 2017, or to one in 2017, have looked at the use of metal material. Some have used, author 2 looked at the use of stack antenna structures. Others have looked at the use of metal materials to actually improve the patch. Others looked at fractal structures. Others also have looked at the use of multi-layer, the use of frequency selective structure. But some of the key challenges with all these existing solutions in literature, others have also looked at the use of stop, use of parasitic patch, and also the use of stop and slot. But the key challenges with all these existing solutions are, one, most of them are complex in design. They are complex in design. Despite their complexity in design, they have limited gain improvement despite their complexity. And when you use stack or you use parasitic patch and so on and so frequency selective structure, the size of the antenna tends to increase. Also, with increasing size of antenna, we talked about the cost effectiveness. It will not be cost effective because you are bringing in more and more materials to the antenna, thereby it's not cost effective. Our aim, we actually aim to design and perform a compressive performance. We design and perform a compressive performance analysis of a miniaturized arc slotted patch antenna for UWB applications. What we did was we designed antenna with a broad band coverage. That means it was covered the range of frequency of UWB from 3.1, putting in mind that size, space is a constraint. So we also designed it to be compact size, and we evaluate the performance of this antenna across the UWB frequency. We also compare this, our design, with existing antennas already. Now, our methodology, there are key things we did to actually achieve our aim. we first of all carry out a theoretical design. We simulated, then we compare our simulations with existing design. And our research is actually guided by the FAIR principle, meaning it must be reproducible at any point. Now, for the theoretical design, we are guided by this design equation of a monopole antenna. Our lower cutoff frequency, which is what we actually require, was at 3.1 gigahertz. And we have, for us to calculate our radius, the formula 2 is used to calculate our radius. Also, there are key techniques we utilize. We make use of defected ground structure or partial ground structure. We make use of slot, and also we make use of groove on our antenna. Now, this is the evolution of our antenna. Antenna 1 is our initial antenna design from the calculation, from the theoretical calculation. Antenna 2 shows our antenna with a partial ground structure in order to improve the bandwidth. Antenna 3 shows our antenna with the groove. Antenna 4 there shows our antenna with the arc slot to actually improve the bandwidth, the gain of the antenna. Now, these are our results. The first thing we did in our antenna 1, if you see, I said the challenges of patch antennas is that they are narrow band. Antenna 1 there initially actually have a narrow band. But with the use of partial ground structure, when we reduce the ground structure, you discover that there's a significant improvement of the bandwidth of the antenna. That's figure 2A there. In figure 2B, we have our antenna 3 and antenna 4. Antenna 4 there is the proposed antenna we actually designed. Antenna 3 there shows us our antenna with a groove. We can see that antenna 3, the S11 is actually a little bit poor as compared to what you have in your antenna 4. Antenna 4 is actually more improved with more bandwidth, and also a good S11. We looked at also the realized, the frequencies against the realized gain. We can see that from the lower cutoff frequency, which is at 3.1, we have an increased gain from 3.1 to our target frequency from 3.1 to 9.6. There's an improved gain. We achieve a peak gain of 6.14 dBi at 9.6 gigahertz from figure 3A. And also we looked at the efficiency against the frequency. We discovered that the efficiency of the antenna increased till we get to 85% at 4.02 gigahertz. Also, this is the normalized radiation pattern of the antenna. The E and H plane at 4.02 gigahertz and also at 9.6 gigahertz and at 11.46 gigahertz. The E plane shows a figure of 8, which implies that it's bidirectional, and also at H plane is omnidirectional, as can be seen from the figures there. Now, these are actually the optimized dimensions of our antenna. From the calculation, we carry out parametric studies before we are able to come to this optimized dimension. In the first case, initially we have a antenna with a full ground, but with reduction of the partial ground. How do we know that if we reduce the partial ground to this level, we will be able to cover the whole bandwidth? So we carry out parametric study, and our parametric study gives us that the radius of the patch that we can use to do this is at 8.8. Also, the length of feed at that point, we have 6.38 millimeter. All values are millimeter. Now, we also look at the far field broadband property of our antenna evolution. Antenna 1, at the initial design of our antenna, we have a peak gain of 1.33 dBi. and directivity of 4.8. The peak gain increases as the evolution of our antenna increases. At antenna 4, we have a peak gain of 6.14 dBi and directivity of 7.2. If you also look at the bandwidth of the antenna actually increases from our initial design to the antenna 4. We also compare our design antenna with other works that are existing in literature. You can see our target is we have a miniaturized antenna with improved gain. If you look, the first one we have dimension, the first design here, we have a dimension of 30 by 30 by 1.6 with a peak gain of 3.9, and down to our design, our lower cutoff frequency was at 3.14 gigahertz, and at the size of 28 by 28 by 1.6 with a peak gain of 6.14 dBi. We can see that our antenna is actually miniaturized as compared to other design. Auto 16 there actually use a stack antenna, and with a stack antenna there is actually more complexity in the design, more complexity, not cost effective in the design. That is Auto 16 here. So our antenna actually have performed other ones that are existing in literature. Now in this study, we have actually done the design of miniaturized circular arc floated antenna. The introduction of modified ground plane or defective ground structure, you can see enhance the bandwidth of the antenna, increase the bandwidth, improve the impedance matching of the antenna. Also, we have in our design, we have a wideband which ranges from 3.1 gigahertz to 12.4 gigahertz, showing that our antenna is suitable for the UWB applications. We also achieve a maximum gain of 6.14 dB at 9.6 gigahertz, which implies our antenna is actually effective in signal transmission. And also, the radiation efficiency is observed to be 85%, despite the decline to 72% as the frequency also declines. We've also done comparison with other antenna, and we can see that our antenna demonstrated superiority as compared to other antenna. In terms of size, we have a miniaturized size. It also has multi-frequency operation, and also our antenna has a high gain. These are some of the future directions we want to look at. I want to also further look at how do we further miniaturize this antenna. Looking at fractal geometry, if we can put fractal geometry on our antenna, what will be the improvement on the antenna? We want to believe that this will actually reduce the size of our antenna while it will improve the signal strength. These are references we've done. Thank you.
Question?
Yes. Thank you for your presentation. You mentioned on your determining the exact parameters that you use the optimization technique. Can you maybe elaborate on that? To actually get to the right dimensions, and how did you go about getting to those dimensions?
Okay. The initial thing we did, let me go back there.
Well, specifically that it was where you refer to the chart with the final measurements.
Okay.
Yeah. This one, those values.
Yes. The initial calculation we did was for a monopole antenna using the equation 1, 2 as I earlier displayed on. So after that design gave us That design gave us the first antenna one we have there. If you look at the board, gave us the first antenna one. That design is actually a very poor antenna. It has a very narrow bandwidth. So what we did next is to actually carry out a parametric study to reduce the ground plane to see if we reduce the ground plane of this antenna, what is the effect of reducing this ground plane. Now we carry out parametric study from the initial height, which is at 8.8 at 28. Then we carry out it out till we get to the size of 6.7. We discover at that point there is significant improvement in the antenna without losing both gain and directivity of the antenna. Further reduction, we actually get a very poor antenna design. So, and also after that, we also look at what are those other things we could do to actually improve our antenna. As you can see from antenna 2 there, we have not actually covered the whole bandwidth that is required for the UWB application. It is from 3.1 we are supposed to achieve to 10.6. We have not covered it, so we look at other things we could do to actually improve this antenna. So we look at if we use groove, what is the effect of using groove? We carry out parametric study on the size of this groove. So we achieved the size of groove at 2.46 was a number that was actually good to actually have antenna 3, and also further we did the art to improve the antenna. I don't know if I answered.
Yeah, no, it's a if you have those number of dimensions, it becomes a multi-dimensional problem. You tune one and then the rest are not optimal.
Yes.
So you follow the stepwise
Yes.
approach. I just didn't completely understand what you meant by parametric, but now I understand.
Oh,
Yeah.
okay.
So thank you.
Yes, please. Yes.
So the manufacturer,
Good.
because it's supposed to be cost effective, so I'm just interested how did it pan out?
Yes. For this presentation, at this point it was at the simulation stage. But you know that the size of the antenna determines what material it will cost to produce. So if you have a bigger size, it implies you require more material and you require more, the cost will increase. So with a bigger size, you have more material and the cost will of course increase because the radiating patch is copper. So with more size of it, you have more increased materials to use, which will not be cost effective.
And what role would the complexity of the design play with your small tolerances? Would that have an impact on the manufacturing cost? Apart from the material
Yes.
cost, the small tolerances you have and the complexity of the design, would that increase the cost then?
Yes, the complexity will actually increase the cost. But in the case of our home, we make it so simple because you just have a cycle, and in the cycle you only have an arc. But if you have a design that has maybe so many chords and so many surfaces, it becomes complex. And when it's complex, it's difficult for the machine production. Yeah. Yes.
What is the more important in your research, gain of antenna or dimensions?
There are two things we looked at: the gain, the size. You don't want to design an antenna that is small in size, but is not actually transmitting all the request signal you want it to take. So you have to look at those factors. We are considering the size at the same time, looking at it fairly that we want to reduce to a size that we are not getting our signal to the point where we want to get it to. So it's more like a win-win situation for the two cases, for the size at the same time for the gain and directivity. You know that if the gain is improved, of course, the directivity is actually improved. I don't know if I answered your question, sir.
Other questions? No, thank you very much. are in time because we have only 6 presentations, so not 7.
Okay.
Well, okay. Fourth presentation is done by colleague Nishiza, sorry. Free-space optical communication link performance based on various transmission schemes over a gamma-gamma distribution channel. I will give a link.
Ladies and gentlemen, good morning to you all. My name is Colette Muchiza, and I'll be presenting a study that is in the era of wireless communication technology, and of course, no ship sails without captains and commanders of it successfully. So my captains and commanders will jump in and review. So our study is based on the space optical communication and performance based on the various transmission schemes over gamma-gamma distribution channel. So the following outlines will be covered during this study. We'll start with the background information until the results, and then we will conclude. So, what is optical communication technology? It is well known as a cutting-edge wireless communication technology that transmits its data using optical signals between its transmitter and the receiver. So it utilizes a line of sight, and it is also a fiberless technology, which makes it a laser-driven technology. So its transmission rate is up to 2.5 gigahertz of data, including audio and video. So that could be 10 gigahertz of data in the near future. Free-space optical communication is first showcasing its unique features compared to the other wireless communication technologies such as radio frequencies and being immune to electromagnetic interference, being able to operate in a license-free spectrum, and thus enabling it to have a high-speed data transmission of gigabytes per second. And of course, one of its important parameters is its link parameters, which is its operating wavelength, as well as the link range of up to 5 kilometers. So, what is the motivation behind this whole study? Of course, the services and applications that have been launched on a daily basis in different devices such as desktops, laptops, as well as smartphones. So what does that supposed to mean? It means now there will be a much requirement of internet connectivity access, and that is leading to a much higher demand of bandwidth and leading to higher demand of data transmission rate. Next question, what does that supposed to mean for our telecommunication companies? So it basically means maybe they will no longer be able to support all these high demands, or else they will have to compensate in laying cables for their backbone networks, or alternatively look at the microwave radio links. But then again, what will happen if these cables are to be laid in the most established infrastructures? That could lead to a problem, of course. So that is why today we are here advocating free space optical communication links and the event of fiber cable distractions. Oh, as much as free space optical communication has all these exciting advantages and benefits, it is of course facing some challenges in terms of environmental factors as well as a link range compared to the other radio frequencies, such as radio frequencies, wireless communications, of course. So in this case, we will look at weather conditions as well as atmospheric turbulences. So weather conditions, what they do is that they cause a signal fading, also known as scintillation. And in terms of weather conditions, we look at the fog. The fog causes signal attenuation and thus degrading the whole system altogether and its reliability. In terms of link range, since it has to operate in a line of sight, that it is limited to short range. So even moving back, they can cause a link outage altogether or motions of the buildings. So our aim is to investigate at least 3 different transmission schemes to to evaluate the link performance, its feasibility, as well as its reliability. So in doing so, we'll be trying to conduct the performance analysis in terms of the key performance metrics such as the bit error rate, the signal to noise ratio, and then of course, if you are designing a link for your communication, it will be fair enough for those designers or let me say engineers or researchers to understand the mitigation techniques to look at in order to overcome whatever shortcomings they have. In this case, we are looking at the effects of atmospheric turbulences and different weather conditions to the propagation of the laser beam as well as its link availability. So some of its applications would be being the backhaul for cellular networks, as we know that technology is advancing, so it will mean that it will be able to support the likes of sixth and the fifth generation. And then it will be the last mile connectivity, meaning it will allow the users to be able to connect into the network in areas where connectivity is highly impossible. And it could be used as a fiber link backup, and also in space applications. And we all know these type of applications, they transmit a very high sensitive data, because of course it has a secure data transmission, because the narrow beams and now it is lower susceptible into interception, and also during disaster recovery scenarios. So during our methodology, we had to characterize the channel and also do the system modeling. In characterizing the channel, of course, I said we are looking at the atmospheric turbulences, the weather condition which is formed, and in this case, in terms of channel characterization, we have picked the channel static model that is using gamma distribution channel, and the reason behind this. And the reason behind the gamma distribution channel is because it is irrelevant to the transmission schemes, which is our modulation schemes, of course. So the gamma distribution channel will also be able to give us a probability density function of the received irradiance. And this is the formula that we have used for the probability density function, and it has the parameters of beta and alpha, which are related to atmospheric conditions. And for the weather conditions, which is the fog, we used the Kim's model. So continuing and implementing these mathematical tools, we have also used a closed form expression that is considering the logarithmic function for these system matrices. And the software that has been used is that of MATLAB. So basically, behind all the parameters that we have, we also have the atmospheric visibility of 2.5 kilometers, the reflective index structure, which measures the atmospheric turbulence strength, that will be considering the width of the turbulence strength. The rate of variance with different variables depending on the link range. Each link range corresponds with each of these rate of variances, which is the measure of the signal strength that will be transmitting during our transmission. So the reflective index structure will be kept constant, and the laser wavelength that we are using is the highest wavelength because it has its own effects on the field performance. So this is just a demonstration of the behavior of our received irradiance during the strong and moderate and weak turbulences. So our results, as we have said, we are going to evaluate a discrete transmission schemes. So in this case, when the distance was at the lowest, which is 2,000 meters or 2 kilometers, the binary phase shift keying has showcased to have performed better than the other transmission schemes. As we increase the distance, our signal fading has changed to be moderate. And our distance at that time was 2,000 meters, sorry. And then the binary phase shift keying as well as the differential phase shift keying, they have a comparable results during this period, and we can see that our bit error rate has increased this side. So it means the link distance has some effects on our performance of the signal. So we further increased our distance to 4 kilometers, and the variable shift keying still has the comparable results as the differential phase shift keying. And of course, our value for our average bit error rate has also increased, and it is increasing more, and this time it was at the moderate strength. So when we increase it to 5,200 kilometers, the fading strength increased to 0.5, so we call it a strong fading strength, where now it is showing that our system is being compromised as the error rate is more of increasing ahead. So in conclusion, as we have performed the free space optical link performance under atmospheric turbulences and weather conditions of Kamaka materials, so based on our results, it was observed that the bit error rate decreases as the signal to noise ratio increasing, and thus that was improving our system performance. But then, in terms of our transmission schemes, binary shift key maintains a better system performance compared to the other transmission schemes, especially during the weak fading strength and the moderate and the strong fading strength, and thus mitigating the effects of the turbulences. But it was not the case during the moderate fading strength, as the differential phase shift keying has shown a comparable result with the binary phase shift keying with an error difference that was at 1 to the minus 9 and 1.7 to the minus 9 at a signal to noise ratio of 80 dB. And also we have observed that the link propagation has also has some effects, and it can also improve the system performance.
Thank you very much. Questions, please?
Hi, thanks for the presentation. So with regards to using the free space optics for, let's say, backhaul or last mile connectivity, what is the actual throughput, data throughput you need to achieve to use free space optics as a feasible backhaul connection?
Or we haven't looked directly on the specific applications, but I was just demonstrating some of the applications that are involved within it, but our focus is in the development of the design of the link performance itself.
Okay, so you did not specifically look at what that throughput would be for each specific application. Okay.
Questions, please? Yeah, I think that's just onto your question. I mean, you're designing a communications link, so this will typically either be a link in its own right, or the idea of it will be to replace another technology like wireless, radio access, or fiber as a drop link. So what target bit rate would you typically look at on your graphs? What would you aim for what is typical for a free space optic system to be usable?
So it depends on the characteristic of the area.
Yeah, because you showed us graphs with varying bit error rates, but to have feasible, you have a ceiling as to how bad it can get before it's not practical to use it as a free space system or a communication system anymore. So my question is specifically for free space optics, is there like a typical line? In wireless it's around 10 to the power minus 5. In fiber it's around 10 to the power minus 9. In fiber backhaul.
You mean in terms of the bit error rate?
Yes, in terms of the bit error rate.
Oh, from what I know is that the acceptable communication bit error rate is up to minus 9.
Is that 10 to the power minus 9?
Yes.
Okay.
Other questions? No, thank you very much. Serious. They have paper. Okay. Open air surface for 4G core network and 4G 5G phase solutions. Directly.
Pigeon telecals, last mile connectivity, bringing it to the doorstep.
We have a problem with one. But it was a presentation.
This man wants to copy your design and print some antennas for us. He wants to know how much it's going to cost him.
Manufacturing.
Less than 300.
Less than 3,000. Okay.
Now, I think what I mean is if your tolerance is quite hectic, because remember the tolerance,
Yes.
you have a measurement in millimeters.
Yeah.
But you have uncertainty. So you say, I want that's only 3 millimeters, but I want to have a certainty of plus minus 0.01 millimeters. It's much more expensive than having 3 millimeters of uncertainty of plus minus 0.11 of the difference of performance. So there's an engineering cost that relates to that, and that's what Aaron was asking. So, but I mean, I don't think that was part of your study at that point. No, at that time. And what's your typical, what's your cost from wherever you get it, obviously? Per antenna, that's expensive. Is it for a one swap with the shipping, or is it? No, we have. Okay, so one swap, yeah. But that's a different flavor. It's good work.
Okay, we'll switch presentation to the last one. Then we'll see this one. Seiko Macondo, review of edge computing in 5G enabled IoT for agriculture application opportunities and challenges.
There will be mine's on the ESP.
Ah, if you are here, but it's not there. The
No,
presentation.
not yet, no. Yeah, let me see if I can manage to. Yeah.
Hence, the alternative is to use the click share. It works with all pieces. Just plug in the click share and you can manage your screen. Yeah. I can show you a presentation.
Very time to have half an hour.
Just before you begin. Okay, that was fine. Good morning, ladies and gentlemen. My name is Icecet2023. I'll be presenting my paper under that series, a review on edge computing 5G enabled IoT for agricultural applications, opportunities and challenges. I wrote this paper under the supervision of Dr. Tarushiko, What's Matos, and Osama Mushia.
It's a little button.
Yeah. On the side.
Yes, on the thumb, the side of your thumb.
Oh, this side?
Yes, there's on and off button there.
Oh, okay. Technology.
What how many academics does it take to figure out?
It's on, and that's the reason my keyboard, that's fine. In coming to the outline of my presentation, I will dive into the introduction and then the overview of the smart farming, IoT, 5G, cloud and edge, and finally the conclusion and the conclusion. Okay, coming to the introduction of the smart farming, it says as the world population continues to grow, so the demand for the food, farmers are under constant pressure to produce more food. And due to that reasons, there's been pushed to adopt to smart farming. And smart farming is all about the application of ICT systems such as IoT, 5G, and cloud-based processes to improve this process of farming, such as livestock and then crop cultivation. And moving to the next one, these are the technologies of the smart farming. As you can see on top, we've got the sensors on this one, we've got the software applications, we've got the communication system there, which is cellular. That one will be our focus area because that's where 5G is found. And then we've got telematics, we've got that one software, and then we've got data analytics solution for analyzing our data. Moving to the next slide, this is the application of the smart farming. We've got the precision farming, we've got the environmental farming. So again, our focus area will be based on the environmental monitoring, in which will be focusing on the geofencing that requires a very low latency or ultra low latency communication. We've got the remote sensing, we've got the agricultural drones, we've got livestock monitoring, we've got smart greenhouses and computer imaging. Moving to the next slide, this is just the overview of the Internet of Things, which is one of the most innovative wireless technologies today that paves a way for a wide range of things to communicate with each other through the use of Internet. And then moreover, IoT technology can be used in a variety of verticals such as agriculture, as already indicated, in the transportation and in automobiles. And then now, the problem that we're having the IoT that requires ultra low latency. As a result, we're integrated 5G into our IoT in order to achieve this ultra low latency. And then now these are some of the components of IoT. We've got IoT devices. These could be our sensors, our Raspberry Pis, and then our Arduino. We've got the protocols, we've got the data storage technologies, and then data analytics. And then coming to our main topic, which is the 5G. And then 5G is designed to provide high-speed data transfer, low latency, and massive connectivity. And then based on our focus is under the low latency. And then now going to the components of the 5G. And then again, we've got the UE, the user equipment. These are the IoT devices. We've got the RAN that provides the connectivity to the UE. So we've got the 5G core, which is again, this one is our interest, because we're more interested on its network functions. And then it says that 5G is placed in the heart of the 5G system architecture, and then enables the 5G readiness to serve 3 GB defined use cases, namely, and then the first one, that's why it's involved, is the one that will be wanting to achieve, which is the ultra low low latency communications. And then this one is for use cases that require extremely low latency to high reliability, such as industrial automation, smart grid, again for our smart farming applications. So we've got the EMBB, and then we've got the massive machine type communications. And then moving further, in emerging markets, SDN and then NVF and massive MIMO have emerged as the key enablers of the 5G. And then what is then brings into 5G is about separating or decoupling control plane from the data plane. This enhances the control of the network, because SDN provides the central the central overview of the network. And then again, the NVF as a complementary technology to the SDN, it seeks to replace the traditional code and dedicated network operation by visualizing these network functions such as the router, firewalls, and load balancers. And last, going to the massive MIMO, this one ensures that we've got the network capacity and energy efficiency by allowing multiple devices to offload tasks at the edge concurrently. Then moving further, this is the difference between the 4G and the 5G. You can see on the peak data rate on 4G it was around 1 gigabits per second, and then coming to 5G is 20 times, which is 20 gigabits per second. Focusing on the spectrum, it's 2 times bigger as compared to the 4G. Then the latency, which is our main focus, at 4G it was about 10 milliseconds, and then we're talking about something that's less than 1 millisecond. Then we can talk about the speed, 25 as compared to 400, which is 60 more. And then now coming to the overview of cloud computing, because remember, currently our core network functions are deployed on a centralized cloud. So as you can see there on the diagram, you can see now between the IoT layer, where we got our sensor going to the cloud, the physical distance there is very huge, meaning even the latency will be very much higher because of that distance. And moving to the cloud, this is the background of the cloud. I won't tell much on this one. And then coming to the edge. Then Icecet this was just computing architecture that enables organizations to use data collection, analysis, and processing at the network edge without direct user interference. Meaning now, as opposed to the cloud computing, this one brings those processing powers close to the sources of data, which is closer to the IoT devices. And then moving further, as you can see on the diagram now, instead of sending everything into our centralized cloud, now it's on the edge, meaning now the distance between the IoT and the edge has been shortened, meaning now the latency is to be low as compared to the cloud architecture. And then moving further, here's the difference between the cloud and the edge. You can see the latency is under cloud is high, and then under edge is low. And then the distance again you see from the cloud going to IoT devices is much higher, whereas on the edge is lower. And then the data analysis takes more time under cloud infrastructure, whereas under edge it is provide real-time data processing. The performance obviously will be slow because of the distance and latency, which will degrade the actual performance of the whole system. Then coming now to actually benefits of the edge or of a cloud, low latency provides local storage, low computational task, local data analysis, and then faster data processing. And then now coming to the potential latency reducing techniques using the edge computing. So the first one will be to position the edge gateway. So on this one, we can position the first one, we can place this based on the proximity, and then says that placing edge gateway near the IoT devices or within the same geographical area decreases the physical distance that I spoke about earlier, that the data must travel, resulting in a decreased latency. Then the second one is distributed gateway deployment. As you know that in cloud architecture, everything is centralized. But coming to this one, we're gonna distribute our gateways to the edge nodes, meaning now again the distance will be reduced. And then coming to this one, so this one is my main topic or my hot topic. We're going to focus on the UPF placement. As you all know that UPF is usually a network function in our 5G core. So this one connects the UEs to the internet. So on this one, the main idea is to deploy the UPF on the edge, meaning now the distance that must be traveled by the data from the IoT device to the core will be reduced, since this one will be placed on the edge. And then moving further, the composition of our study, it discusses the edge computing reducing techniques, and then outlines the challenges faced by the cloud-based 5G architecture, whereby all network functions are centralized. And then coming to our conclusions. So this one, we say that the edge computing has the ability to address the shortcoming of the centralized cloud architecture by offloading the UPF function to the edge. Thanks.
Thank you very much. Questions, please? Yes.
Yes, thank you. Great presentation. I've been involved with some farming-related topics, but mostly sensor systems. And one of the problems is that many of the farming systems have already infrastructure installed, like sensor systems at least. I know I've been involved with one which has got picking robots. And now that's quite a different thing. Maybe Edge works very well for that. But with these sensor systems, LoRa is like the go-to solution for that. So I'm wondering, if you're suggesting switching over to 5G, for example, is that something that could integrate with the LoRa system? Would it only be a hub to the 5G, or would there be some way that an actual whole set of farms that are set up with LoRa could cheaply be transferred over to a higher speed 5G infrastructure? What's your view?
Okay, thanks for your question. Yeah, initially I've been really thought about integrating the two, but as we have mentioned, I think it would be a great thing to try to do that too. So going forward, I will also consider it. Thanks.
Any questions? I have a curiosity. Do you think that a fog layer between edge and cloud would be useful to solve some problems in this area?
Yeah. So now, I also thought about.
And did you take in consideration this second layer in your research?
Sorry?
Did you took in consideration this fog layer in your research, in your study?
Not really.
Not yet. Maybe an idea for the future. Okay, other questions? Well, thank you. Okay, so our last presenter. Last Kazi, open air interface for 4G for network and 4G 5G based.
Hi everyone. My name is Mlav Vilazi. So today I will be presenting the paper that we wrote with Professor Ulwan, Professor Luzamo, and Professor Albert. So the title of the paper is Open Air Interface for 4G Core Network and 4G 5G base stations. So here just shows the agenda of the presentation that I will just take you through. So I will talk about the abstract research objectives, testbed implementation and requirements, design overview, setup and performance result, and I will also conclude with the summary and future work. With the advance of fourth industrial revolution, 5G networks are aiming to support a broad range of network services and applications. Network operators are looking to open source implementation to expand on the flexibility and the reprogrammability of networks. So this paper shows the steps followed to have a complete 4G 5G mobile network using open air interface. The paper also introduces the implementation, including the 4G core network and the OEI 4G and 5G base stations, and also the 4G and 5G user equipment. We use the Wireshark software for packet visualization when the two base stations connect and disconnect to the connection, and when the phone is attached and detached from the network. Additionally, some installation pointers, current performance statistics, and video streaming such as measured download speed and latency between the various components are also included in this paper. So the objectives of this research is to implement a customized 4G and 5G radio access network for experimental work. Also to implement the OEI 4G RAN and OEI 5G RAN and ensure that the two RANs can establish connection to the OEI 4G network. And also to use the Wireshark simulator to report or show the time when the device is attached to the network. Testbed implementation and requirements. The Unode B and Gnode B base stations machines run on Ubuntu Linux version 20 and use the Open Air interface version 2.0 on a Dell Precision 3630 with an Intel i9. The Open Air interface 4G and 5G RAN architecture to be implemented will likely depend on the I4G connector. Two pointing only to a antenna, one for transmission and the other for reception, are mounted to the USRP 2944R, which is a software-defined radio. And also the user equipment is presented by a dual connection Huawei P40 Pro with a SIM card that has been carefully customized. So here is the high level of a system design that we have. As you can see, we have OI configuration there and the 5G configuration and the OI network and the internet, and also the switch to connect the network and the 5G test bed and also the 4G test bed. So the 5G depends on the 4G test bed. So the communication between the network and the 4G test bed is established via S1 interface. The connection between the 4G test bed and the 5G test bed is done via S2 interface. Then here it just shows the equipment. In our case, we used the Huawei P40 Pro to connect to the network. So setup and performance results. So this screen shows three machines whereby we have machine 1 for the core network and machine 2 for 4G base station and machine 3 for 5G base station. So under machine 1 we use the OI core network code that was stored directly on the latest release tag. Then machine 2 clones the OI code git repository into a desired folder. Machine 3 chooses the steps followed in machine 2, where we use by cloning the OI git repository, check out and develop bench, then running the build commands. So here, these are the print screens from our result. But here we're doing the configuration of the main parameters for our test bed. So this one here shows the main parameters that we configured, which is S1 interface. As you can see, this IP address and the mobile network country code and the I forgot this one. It's mobile network code, and this one is mobile country code, and also the tracking area code. So all these parameters we program them on the core network, on the 4G base station, and also on the 5G base station. And also here it shows when the laptop was used to program the system using SIM card. Because also on the SIM card, so that the phone can connect to the network, we need to program the SIM card using these three parameters here. So here it just shows the print screen where these 4 devices, your core network, your OI 4G base station, 5G base station, and the phone. Here they were communicating, so we used the Wireshark software for packet visualization. So here also, these are the print screens that we taken when we taking the measurements in the lab. So we used 3 applications to test our test bed. So here we used the video streaming using YouTube. Then here is when GTAB laptop was connected to the Wi-Fi hotspot of the Huawei P40 Pro. Then we were connected to the meeting using MS Teams. Then here we're just testing the performance of our test bed. So what we used to test the performance or the speed, we used the speed test. So we're checking like the download speed and upload speed and also the ping. To to summarize and also future work for this paper, the paper details the setup and tips for solving several practical challenges. We used mainly the Wi-Fi 4G and 5G RAN and Huawei protocol, user terminal and a GTEC laptop. After facing several problems, successfully internet connection and usage of online applications such as Microsoft Teams, TeamViewer, LaTeX Overleaf, Zoom, were also achieved. For future work, we will use this testbed to develop a vertical end-of algorithm open air interface and the application of remote piloted aircraft systems as a use case. Okay.
Questions, please? Minutes?
Thank you for the very insightful presentation. I think one of the things here is, so you're experimenting with the test bed, so I'm curious, especially with your future work, how do we navigate or go about the licensing issue of using frequency or spectrum to do your tests? Is that something that's addressed in the paper, or?
No, it's not addressed.
Yeah.
It's not addressed. So currently, this testbed was done at the chamber. So we have the chamber there, the CSIR. So we're just connecting everything with the chamber so that we can access.
Other questions? No, thank you very much. Before concluding, I want to invite at the registration desk, there is a call for paper for a conference we had in Romania in the middle of next May. We have the call for paper, you are all invited to come see Dracula. Thank you very much.
Yes, did you get that?
No, we check.
Okay, thank you.
Maybe
People are actually here, but I guess okay. Thank you.
Simon, the laptop will remain here.
Yes, yes, yes.
You can.
Presentations, are you both from YouTube? Optics. It normally replaces 5A. So 5A is the now 5% of the A for 10 to the power minus 1, which is 10 to the power minus 6 is 1 in every million bits. So wireless systems is bad with 10 to the power minus 1 in every 100,000. That's a mistake. So you can't design your email code, the stuff that runs on so that's what my question was really about.
It must be sorted.
No, we can't now.
It has been known, but
It's fine, it's in the moment. And then looking at your results, taking that into consideration, what did you say is the practical length that you can get with your Yes. Anything above that it becomes troublesome,
So it's how much, man?
Which seems, at least from the little bit I've read about it, to be correct. That's where most of those systems, if you do the calculation, that's where they end up. Something that was
and maybe it's because it's remote, but something like this. What does your work and
Huh?
maybe what does code maybe check on that.
Cutting court. It's expensive, that one.
That's why
At least.
The boss, that email is
Huh?
that email
What?
that email from
Correct. There was no choice. Otherwise, if we kept quiet.
it's more about comfort or well-being.
Yeah, it's true. But even if they correct, there is not safe. Actually, we're supposed to look for a police station. Then
So, I don't know if it's something about simulation.
from where? To tell them that we slept at the police station, why not a garage? So they need to know the truth.
I'm around for garage for sure, they pay me below the skies.
Yeah.
I'm not saying your work is wrong, that's not what I'm saying. I'm just saying maybe have a look at it, you know.
Yeah, for me, I think next time if I have to travel, I will make sure that everything
It's
is
fine
sorted.
before you leave.
Yeah. And that one is expensive. Getting cooked.
So for today, tomorrow, tomorrow's what?
Huh? Tomorrow Friday.
It's 2 days now, yeah, tonight. It's like 4.
4,000 for 2 days. It's more compared to what they said. 14 days. Because one night, it was just one day. We're supposed to post
Another session.
You must just check that the better rates that you are actually getting a situation which presents reality. You know, so it might be that the power setting in your simulation is too weak for you. There's a few things that can cause it because the curves look right, but the error rate doesn't look right to me. That's just an observation. If you say it's the wrong curve, then it's just you're getting the wrong thoughts for
But I have to say some of the challenges we had was
but in any case, that's my 10 cents years ago.
getting that to the university.
So the easing for your work.
Yeah, we got it
actual
up and running, and our UE was a USRP,
and
and
use the actual parameters for that region.
that was a UE with didn't get some cards yet.
Test, and if you can get your
Actually
hold on
got
the
the
system,
that
that
for
is
the UE, and it connected and made it established the connection and everything. But to go and then by getting traffic out of
worked a lot on
to the
the
internet and
the modeling of the and we worked on the microwave links, the modeling of the microwave links. Come again?
yeah, it's
Yeah. The name will come to me now.
Thank you so much for that. A lot more information.
We will, most probably. Yeah.
Okay. Good presentation, how are you? Good. We meet again, it's more, it's about a year ago.
I told him.
Yeah, I'm saying we're trying about I'm really curious, how you guys, you have license? No, actual testing, not yet. Still waiting. Wow. Yes, that's it, okay. Sure. But yeah, it's cool to see what you guys are doing up and running. We're also playing around with the stuff based on your recommendations. But we want to upgrade our hardware, so we... No, we want to do a real phone, but we have a... I will still buy a sim emulator. So we can get the Cube Cell 1 or whatever. And then we have the USRPs as UEs currently, the emulator. We have some B200 minis that we emulate as UEs. We can do the sim emulator. Now that would be quick. The part that's giving us the headache is getting the call to talk to the internet and getting the US to the internet. Yeah.
So we have students who are going to
We did actually we had a student, we had contacted him, he was finished early with his masters, and we had about 2 weeks left, and in the 2 weeks he said, now he wants to figure it out. But we have 3 new guys coming in next year, which I hope to actually put on a full time. Yeah, because you need the platform to do work. Yeah, no, but it's also been a bit of time. But so I did a bunch of like,
Yeah, but they go inside. Yeah. How are you? Nice to meet you. You have a second chair?
Yes.
Nice. Yeah. Yeah, that was very spontaneous. Oh, very nice. I'm here since Tuesday, so I had like 1 day to check the area. Amazing. How long are you here? Okay. Awesome. I have to leave on Saturday, so yeah. Yeah. Yeah, I like it so far. I've been to the waterfront like every evening. To the wetland? Okay. Nice. Amazing. Like hybrid electric vehicles and modeling, operating strategies, stuff like that. Yeah. Maybe. What's your field? Okay. Yeah. Excited about your car. Let's see. Yeah, they're big in Germany. That's cool.
Yesterday we arrived and now Do you have WhatsApp?
Я думаю, так даже лучше. Я согласен.
Not working. I'm.
Да я не думаю, потому что он из этого прожектора.
Thank you so much.
Yeah, couldn't add my name here.
Oh, sorry. Yeah, now you can. Which city do you live in Germany?
Excuse me?
Which city do you live?
Kaiserslautern.
Do you know Professor Ralph Kennan?
What's the name?
Ralph Kennan. Ralph Kennan.
Like which university is that?
Munich.
Munich, okay.
Yeah, Munich.
What's his field?
Exactly sensorless control.
Okay.
Yeah, I published one paper with him
Nice.
in the German.
Yeah.
And next year in January, he will come in the South Africa for the South. There is a big conference in the South Africa, in South, and he will come.
Yeah.
Because our university invited him
Nice.
for the conference.
That's cool.
Yeah, he's very famous professor in the world, Ralph Kennan, in terms of the model predictive control and inverter switching, and like that.
Nice.
Yeah, very nice.
That's cool.
Okay.
Yeah, just send me a text with your.
Yes.
Yes.
Is that correct?
Yeah. Perfect.
Yeah.
Perfect. Thank you.
It was good to see you. Yeah, thank you. Hello everyone, this is the session B, and we have 8 presentations. Two of them is for one, and the first presentation is from the, I think, professor, yeah, Professor Vladimir. Yeah, sorry, yeah, we can start.
Paper number 72, control of resource with pulse width modulation. And this you can see also. Introduction. We have this block diagram for controlling of resource with pulse width modulation. So this we have reference signal, feedback, and we use Arduino microcontroller. Output signal after Arduino is pulse width modulated. And this we have linear part load. And first we will consider open loop control system with discrete modulation. In this case, we see pulse, output pulse signal, and we see analog feedback signal. And for analysis this control system, we can use difference equations. In difference equations, we need to find solution from Vn to Vn plus 1. So we have these two differential equations. When we have pulse, we consider first order when we have RC circuit, first case when we have DC voltage source, and second when input signal 0. So we solve this equation, difference equation, and we can see this solution during 15 periods. We see that this signal very resemble to real signal. We consider two cases. First case with amplitude modulation. In amplitude modulation, amplitude signal with source equals gain multiplied difference, reference minus feedback. And difference equation looks like this: Vn plus 1 lambda Vn v Vr. And solution we have in this form, C multiplied lambda in the power n. And we have this root locus as function of gain in control system with amplitude modulation. And we have two cases. First case, we have roots positive, we have 0 roots, and we have -1 level. So when we change gain, we go through these 3 zones: real roots, 0, -1, and less than -1. And by using this simulation, MATLAB simulation, we can see these cases. First case, we have figure number 8, transient response with positive root locus. We see that we have this transient response and then steady state value. What is important is we do not have frequency of output signal. Second case is 0 value of root. When we have 0 value of root, transient response during 1 period. So we have this transient response, and through 1 period steady state. And next, when we have negative root between 1 and 0, in this case we have case when output signal has frequency 2 times less than amplitude frequency. And finally, when we have root negative, we have frequency less than previous, less. That is the main problem. And let us see next. Next, control system is pulse width modulation. In this case, we have low modulation. So Tm equals reference minus Vn multiplied gain, K. And figure number 12 shows scattering chart Tn plus 1, Tn. When we have pulse width modulation, this chart non-linear, and we see this orange non-linear. We see this non-linear flows to linear, and that is why we can use linearization. And next, we use linearization in linearized case. So we have this delta Tn plus 1 equals lambda root and multiply delta T. And we have actually analog to previous this function of gain in control system is pulse width modulation. So we have when root equals 0, minus 1, more 0, less minus 1. And actually we should receive the same result like in amplitude modulation. So this we have simulation control system with pulse width modulation. First figure 4. We have positive roots. Positive roots, it looks like this. Figure number 14. And figure number 15, we have transient response with 0 value. So this we have, when we have lambda equals 0, transient response equals 1 period. We see this 1 period of steady state. And next, when root locus between 0 and minus 1. Between 0 and minus 1. So with this have frequency equal half period of pulse width modulation. And finally, when we have root less than minus 1. So in this case, we have frequency response less than in previous case. And this result we received by using analytical solution. The same result we can receive if you use numerical integration technology. So for solution this differential equation, we can use Runge-Kutta digital integration program. So in this case, we see a result like in analytical solution. Experimental verification. For verification, we use this in the middle microcontroller Arduino. Output signal of Arduino is pulse width modulated. Then we have this power driver and DC voltage source below. And we can receive the same result like during analytical solution. So last case when we have lambda positive, next when we have lambda between 0 and -1, and finally we have when lambda changes less than -1. The difference, conclusion, the different equations are advantages to describe amplitude and pulse width modulated control system. They are convenient for simulation considered control system and analytical determination of their dynamic properties. The difference equation solves the differential is solution of differential equation describing the control system in interval 1 period. Control system with amplitude modulation are linear, but with pulse width modulation non-linear. We show that the non-linearity of the differential equation is not significant and can be linearized in points of steady state condition. The root locus of control system with first order linear part can be a positive equation equals 0 or negative. The stable mode exists for only positive roots when root equals 0, more than 0. When the core is 0, the transient response is shortest and equal 1 period. The frequency pulsation reduced to half when the root is between 0 and -1. The pulsation frequency decreases more of the root if the root is less than -1. The Aliasing phenomenon allows explain the instability in case of negative roots. The experimental verification result of the investigation are received. Thank you very much for your
Thank you so much. Time for the question. Okay. Thank you so much.
Thank you. Thank you.
And the next presentation for Henry. Henry? Yeah. With the title of Matrix Converter Gate Driver Control Circuit Design. Do you have flash to transfer the presentation? If you transfer, it will go to the class. Is there? Yes,
Раньше не давали закладчики. После предыдущего, в прошлый раз. Так, вот.
Chair. Good morning, colleagues. My name is Henry. I will present a paper titled Matrix Converted Gate Drive Control Circuit Design. This is what I'm going to be talking about. As far as the introduction is concerned, I would like to mention that I focused on the direct AC to AC matrix converter. This type of converter does not have a DC link. It's a direct AC to AC conversion system. Normally, researchers focus on AC DC matrix converter, which has a DC link where the capacitor is basically an energy storage device. There's various applications for converters and advantages associated with it, one of which I've just mentioned. It's used in VFDs, AC-AC converter, direct AC-AC converter has this advantage that you can also have a bidirectional flow of power. But like I said as well, if you don't have the DC link, then you can be able to achieve the minimization of the size of the converter. I've just mentioned a few control methods. There's a number of control methods, a lot of them actually, among which you have space vector modulation, logic modulation, and other methods which I have not mentioned here, but they are used to manage a converter. So in this paper, I've focused on designing a gate drive system that enable us to switch or control the converter, which I think can be achieved in one of two ways. It can be largely software, or it can be a combination of digital and analog electronics to when you design the gate drive circuit. Let me just mention what the issue is. The issue is that if you have a basic circuit like this, this is a basic topology of a converter. If you have a circuit like this, you do not want to switch on any of the two switches at the same time. In which case, you will basically be causing a short circuit between any two lines or any three lines for that matter. Secondly, the load is considered to be inductive, which means that if you turn off any of the line switches, you actually create an overvoltage across the load, which is also undesirable. So these are two main problems which are associated with the direct AC-AC converter, which most researchers have basically tried to solve or avoid. Like I said, this is the basic topology of it. This type of converter is basically realized by creating a piecewise construction of the output voltage by picking on each of the three phases one at a time, as described in the previous slide. Where in this model, beta, basically you can call it the control angle or the duty cycle.
this duty cycle is such that it's basically a third of the full period weight of the switching function. And so, as you can see, we basically divided the switching into three pieces where we click on each of the phase voltages sequentially. And this top is basically the definition, where we have this definition of the output voltage for the first cycle. You obviously can rewrite it differently for infinite, if I can put it that way. And like I said, you would over here, sorry it's not quite visible, but basically it's just showing the different states that you will have, your switching states, where you would switch from one phase to the next. And before you switch on to the next phase, you would obviously have to leave a dead time of some amount, a constant dead time, which is safe enough for you to be able to switch, like I said, across the load. So I was saying that I focused on developing this using a combination of analog and digital electronics, where if you look on the far right, I show the ring counter that we used to incorporate when building the circuit with three flip-flops, D flip-flops over there. And obviously down there at the bottom is the Fourier series coefficients for one of the phases, for example, like the origin or the others, right? I just showed the Fourier coefficients for one of the phases. And so we come up with this particular circuit shown here in the center, where we were able to produce the required wave shapes for us to be able to feed to a power circuit that I showed previously. I've not yet realized the output wave, but that's what you can do later on to check what actually happens. Although we have we've implemented this in an experiment. Just for clarity, I needed to just reiterate that this is a variable duty cycle. These are a variable duty cycle, but it is a constant. It's a third duty cycle, but it's a variable duty cycle, if you understand what I'm trying to say. It doesn't show clearly, but between any of the successive pulses from one to the next is a dead time of some amount. You can see that clearly from the graph here. The top ones are the three wave shapes before we process them, and the bottom small ones are the wave shapes after processed, which we use to switch on our power. Switch on to our power circuit. I've showed this in this table so that you can see clearly. We've left about 0.1 milliseconds dead time between any successive wave shapes. And in this measurement, we had about 0.9 and 0.8 duty cycle, which I said is very could be something else depending on what you've done to your protection in terms of variable duty cycle, which if you were, for example, applying this to a machine, an induction machine, you would be able to control the speed of that machine. Like I said, what we've not done as a recommendation, which actually we have done, let me put it that way, we had not done it when this paper was written, but to apply this control circuit to a power circuit, we've done that with a 0.18 kilowatt motor to check if we're able to control the speed of the motor, which we were successfully able to control. And one of the things we're concerned about was it going to work, which it did work. We expected smoke because you are basically switching very tightly and you need to be very careful when you do the switching. But we were able to apply this to a small induction motor and we were able to manipulate the speed of the induction motor. Then, like I said, we will do some more analysis and things like this to see what actually is happening, and we will try and get some more research, maybe articles towards that. So in conclusion, I wanted to say that a simple and concise gate drive circuit was designed and implemented using electronics circuit combination and a bit of programming on the computer. And we've managed to solve the famous problems of commutation, which are over voltages whenever you have switching across inductive loads and short circuit currents whenever you are switching two lines together. And so I would like to end it by saying this was we think, a fundamental approach to a matrix converter. I've seen other researchers do have complicated ways of doing it, but I thought, why don't we look at a fundamental approach to it and let's try and solve it that way. So, thank you, Chair.
Thank you so much. Do you have any question? Yes?
Excuse me, what about noise stability for your device? Do you think about it or no investigation now? Noise stability.
Stability of the noise.
Well, there's not been, like I said, this is a fundamental approach to this. Whatever we predicted would happen actually happened. So we didn't have any form of instability, if I can put it that way. I have not basically analyzed completely what goes on, but it seems to me that there are ranges, if I can put it that way. There are ranges within which you would have conversion. There are ranges within which the converter actually doesn't convert, it actually inverts, if I can put it that way. So for example, if you look at it at 3 pi by 2, for example, that's where you start to get changes, you see, for example. So you just have to look at what happens between 3 pi by 2 and what happens after 2 pi going forward. In fact, after 2 pi, there is no conversion at all. You're only picking each phase at a time, depending on how long your duty cycle is. So that's what basically happens.
Any question? Sorry, I have one question.
Oh,
because also I'm working on the switching for the inverter. My question is that can we develop this method for the multi-phase inverter or converter?
Good question. Yes, like I showed you, the basic topology is the basic topology, which means if you want to develop for three-phase, you can easily do that by simply taking them together. So what I showed you was just the basic. You would just add the same basic to the first basic to get the third and the fourth basic to get the multi-phase. But the principle will be the same. Regardless of whether you have a three-phase, single-phase, a three-phase, or whatever other phase or whichever other phase conversion. The principle of switching is basically the same.
Okay. Thank you so much. Is there any question?
Who wants to take me? That's a gift to my wife.
Okay. Next two presentation is for silicon motor. Yes. Yes, if you want to.
Oh, I see, I see. Good morning, everyone. As the chair said, I'm actually presenting two papers today, but they share a common background. So essentially, given the 6-page page limit, we chose to actually break them up because the first set of findings is more specific to the problem, and the second set of findings has to do with the novelty of the first set of findings and how we can implement it at the hardware level going forward. So we're all in Cape Town, as was well publicized worldwide. Cape Town went through a severe drought